Ladies and gentlemen, thank you very much for subscribing for our joint webinar about instrumented fuzzing, which is a collaboration project between Continental UX and Code Intelligence. And unsurprisingly, our topic today is how Continental leveraged instrumented fuzz testing and ASPICE for cybersecurity to comply with ISO 21434. Our presentation today consists of two parts. In the first session, we will hear the reasons why instrumented fuzz testing is important from the security and compliance point of view. And in the second part, we will explain how Continental built an automated security testing process as part of a scalable CI/CD infrastructure by applying instrumented fuzz testing at the software in the loop level. So at the end of the second part, there will be a little demonstration how an ideal setup looks like from the developer's workflow point of view. And after that, as discussed, we will have a short Q&A session where you have the opportunity to ask us anything. And before we jump straight into the topic, allow me to introduce our speakers today. And most importantly, our two guests, Dr. Michael von Wengstern, who is a mathematician as background, but holds a PhD in software engineering from RWTH Aachen. And he started to work at Continental in June 2019 as a security and privacy manager. And one of his very, very big projects starting at the end of 2019, even before COVID started, was to evaluate the different solutions for fuzz testing out there, which may or may not be needed for ISO 21434. And this eventually led to our collaboration. And since October 2023, Michael is supporting Eckhart to define and improve the security processes across all the different projects within that business unit to be also compliant with the current norms and regulations at the same time. And our second speaker today is Eckhart Heine. He is Product Cybersecurity Officer at the business area UX and Global Head of Security BA UX since 2021. He is responsible for all areas for security and privacy across all the projects coming from the software from this department. And he's responsible not just for development, but also for the production and maintenance of the products. He is within Continental since 2002, and he has seen all the different aspects of software development, security processes in the past. And being a developer himself at some point, he now guides the new generation of software developers to build secure products at scale. And the least important today, I will guide you through the session, through the Q&A. I'm Sergey Dichant. I'm the co-founder of Code Intelligence, and my goal is to enable product teams to enable and automate large parts of their security testing process. And with that, handing over to Eckhart, first of all, telling us what kind of products they secured with this approach. Eckhart, the stage is yours.
Thank you. Also, a warm welcome from my side. So let us have a look. I have here a short presentation only to introduce the products of the business area user experience. We are developing displays, means driver information display, comfort information. Digital cluster generation, which is going down now in the automotive industry. And we have also here some, I would say, innovations, which we have here with a 3D natural display and also the quite news of the shown in the CES 2024, this crystal display. This means the display is completely included in a Swarovski crystal, and this is for which kind of products we are developing in user experience. We would like now to our topic for today, this instrument fuzzing, how we are implementing this in our products as a kind of security validation test method. And with that, I would like to take over to Michael from Wengstern, who is my colleague in responsibility of the governance part in user experience.
Yeah, so now I have a overtake, let's say, for the first part. And here it's important what is the added value of instrumented fuzz testing for security. Okay, so in September 2017, the UN regulation 155 uniform provisioning concerning approval of vehicles regards to cybersecurity entered in force. Yeah, and in this regulation, cybersecurity means a condition in which the road vehicles and their functions are protected from threats. Okay, and then also this regulation is about the cybersecurity management system. This is a systematic risk-based approach defining organizational processes. So it's about processes, yes, what you need to do to be compliant. And then if a vehicle, let's say type has been approved by the approval authority, it's a technical service in different countries, where it also receives an approval mark to show to end customer that the vehicle's type development process includes the cybersecurity management system. Okay, for this talk, let's say for the OEM, the most interesting paragraph is 736. The vehicle manufacturer shall perform prior to type approval appropriate and sufficient testing to verify the effectiveness of security measures. Yeah? So this means it must be tested before it can go to the approval. Okay, for us as Continental, as Tier 1, let's say the section 732, the vehicle manufacturer shall identify and manage for vehicle type being approved sub-supplier related risks. Okay, then based on this UN regulation, let's say different countries and regions, let's say started to update their type approval requirements. First by European Union and Japan. But since Continental is a German European Union company, let's take as an example the UN European Union regulation 2019-2144, let's say, which got updated in November 2019, which is on type approval requirements for motor vehicles. Let's say in this requirement for the European Union, yeah, for the business area, the table D onboard instruments, yeah, as you saw our instruments before, which Eggert presented, and including cyber attacks is relevant for us. That's this European Union regulation has two deadlines. So the first was in July 2022, which is already passed, but this was only for new vehicle types, so which were just rolled out. The more interesting, let's say, deadline is this year in July 2024. And this is for all new, let's say, vehicles, let's say, produced. So that's also the reason, let's say, why some car makers already announced that they stop selling their older car architectures in the European Union, because car architecture was developed before the UN regulation was released. And so, let's say, we are not compliant with cybersecurity here. Here I have an example from Handelsblatt. And here you see that Porsche announced in December 2023 in Handelsblatt that they stop the Macan, let's say, with petrol engine. Yeah, because to upgrade it with cybersecurity would be too expensive. Let's say. So of course later on a new Macan will come out, and this will, once the electric variant will satisfy the cybersecurity regulations. Okay. So not to, this is quite new news here from March this month. Let's say there are also not only Porsche, but also smaller cars like VW Up or Transporter's T61 will not be available in Europe due to the cybersecurity law, which is required for that. So here on this two newspaper examples, you already get a feeling, oh, it's really important here. It's really important for the OEM to satisfy the law so that he gets approval for his types. Okay, now how is ISO related to that here? So the ISO 21434, it's not a norm, but it's a guidance for processes here that also suppliers should satisfy, so that the OEM can say, oh, when they satisfy it, I have the evidences, and this I can take to the approval authority, yes, that I tracked, let's say, their processes, which we do TARA and so on, and do security testing. Okay. Besides ISO, there's also VDA, yes, ASPICE for cybersecurity. It's 3 years old, published in August 2021. And this is the same as ISO. It includes processes for that. But additionally, let's say the VDA also includes a model how to rate it. So that you get then based on that a rating of your processes, how capable it is. This is the capability level of automotive ASPICE. And some the automotive OEMs, let's say, require for Tier 1, let's say, to pass such an assessment with a third-party independent assessor, so that you get, let's say, a document which they can use for their approval authority. And so here, with an independent assessor, we checked all processes, and our Tier 1, all Tier 1s of the car passed it, and we as OEM also. Now we can get our car, let's say, on the street. Okay. Now I explained you, let's say, the UN 155 cybersecurity regulation, the European Union law and its impact that car stopped. Now let's take a look what is for us is Continental, very important. This is the ISO 21434 and of course the VDA ASPICE norm. Okay, when we take a look here, we have the recommendation ARC 1012. This says testing should be performed in order to confirm that unidentified weaknesses and vulnerabilities remaining in the components are minimized. Yeah? I want to say you can never be sure that you don't have any vulnerabilities or weakness in it. You just can do your process, yes, to minimize it. Yes. Okay, now let's take a focus on Node 7 now. So Node 7 suggests a testing message which can be used for us to think pragmatic, yes, to make our assessments later easier. We at UX decided, okay, we first want to investigate with a security testing method mentioned here and to see if this are applicable and find issues in our product here. So we focused on that one so that it's for us easier in an assessment to explain what we're doing. If you now do anything completely different, you need to argue with the assessor. Yeah, so make life easier, we follow that one. Okay, let's come shortly to this, what it is here. We have functional testing against requirements. This is what you know, for example, to verify that your IIS crypto algorithm is correctly implemented. So we have vulnerability scanning. Yeah, I mentioned it here because some people also ask, let's say, before the webinar for SBOM question here. So vulnerability scanning, we use, let's say, a tool based on source code and binary to extract our software bill of material. And then at UX, we have an internal database. And then we also connect to external databases, for example, NVD, National Vulnerability Database. And with that, let's say we can use our SBOM, which we figured out, and also which we verify our Tier 2 suppliers, what is in it. And then we can check based on this databases, do we have any, let's say, weaknesses, which is there known. Okay, and so the third part, which is important for this talk, is fuzz testing. Yeah. So it's very interesting when you also take a look at the NVD. Yes, so the most vulnerabilities which are mentioned there, yes, the root cause is buffer overflow or anything with memory violations. And this is where fuzz testing comes in. Yeah, that's our security department offers interface and instrument fuzz testing, and the aim is to detect critical buffer overflows. And of course, when we find a bug, let's say, or vulnerability with fuzz testing, and we know the element, yes, the SBOM element, when we feed it back in our internal databases, and other projects also can benefit from it. Okay, and then the last point is penetration testing, which you can do. Yeah, penetration testing is where you give your, let's say, ECU, in case our display or head-up display, let's say, to a company which aims to be similar like hackers. Yes, they try an investigative approach and try to hack it via reverse engineering, sniffing, and so on. Yeah, everything is allowed, but also the hacker can do. Okay. Now let's take a look at ASPICE assessments. And here we see ASPICE assessments also check fuzz testing. Yeah? So for us to pass the assessments, it's good when we follow, let's say, fuzz testing. Okay, so ASPICE for cybersecurity is the same. That's similar to ISO 21434. But what it did, it separates it. Yeah, it separates functional testing and the other testing methodology, which I mentioned before. So functional testing is in Chapter 8, Sec 3 risk treatment and verification. So I think the reason is because functional testing is more against requirements and you want traceability, that everything is covered. And here as other test methods like vulnerability scanning, penetration testing, and fuzz testing, let's say they are part of Chapter 9, Sec 4 risk treatment validation. Just to give you some time, there's a question, oh, is ASPICE like an audit? No, ASPICE assessment is not an audit. Let's say because ASPICE assessment takes much more detailed approach when it's done in an audit. Yeah? Instead of just saying whether you pass or fail, ASPICE considers many parameters, also called generic and best practices, and you must prove, let's say, your processes on the concrete project. This is also what is so interesting for the OEM, because you concretely evaluate, let's say, your project of your component, which is then used in the car. So you must show the evidences to the assessor, the process outcomes. Let's say, so this means here in an assessment, we also must show, let's say, our fuzz testing outcome to the assessor. Okay, yeah, this slide I want to say I overtook from René. So thank you, René, for providing this slide. So we at UX have two kinds of fuzz testing: interface fuzz testing, instrumented fuzz testing. Let's say the advantage of interface fuzz testing is that it's executed on the concrete hardware, so system. So this means you can also detect hardware-related issues like in the processor's ROM code. Okay, but this talk covers instrumented fuzz testing. Okay, for me, what is one very large advantage of instrumented fuzz testing is that you can execute it, your software code in the software in the loop simulator. You can think it's like a virtual machine for your automotive OS. And this on a server with many cores. Yeah? Such an Intel server then, which you also have here, is then 100 to 1,000 times faster than our processor into our display. Because the processors in the display, so just that you get a feeling, have around 80 to 160 megahertz and are single or dual core. And so this means on the same time frame, let's say when we simulate it with our simulation in the loop approach, let's say the instrument fuzz testing framework can create much more, let's say, input vectors to attack our system when we could do it with interface fuzzing. Okay, but what is now my favorite part of instrumented fuzzing? Yeah, it's that finding the root cause of instrumented fuzzing is so easy. This is really my favorite. Yeah, of course, as manager, if it goes easier, you save budget. Okay, because since it instruments the source code and it knows directly where you are, then when you have a buffer overflow, for example, in your mem copy command in your source code, the tool of contingents directly points to this position. And this means you directly know where did this buffer overflow happen. In contrast to that, let's say with interface fuzzing, you send CAN Ethernet messages to that. And then what you do is you observe here abnormal behavior, for example, crashes, let's say, of your display. When you see, oh, my display suddenly becomes black. But now the large question is, why does it become black? You know, you still, let's say, error analysis and so on. Yeah? And with an interface fuzzing, it needs circa 1 week, but as an instrumented fuzzing, you need around 10 minutes. That's it. You can take a look at the stack trace. And so you are also more efficient to fix it. Okay. Then I want to say for the ISO 21434 norm, also it differentiates between two kinds of fuzz testing. So see here T1 and T2. This is based on the cybersecurity assurance level. Yeah? CAL, where CAL1 is the smallest security level. This is similar to ACLA in safety. And CAL4 is the highest security level, which is similar to ACLD safety. And as we see here, let's say for the lowest security level, let's say fuzz testing is not even necessary. Then for the second lowest security level, CAL2, let's say fuzz testing T1 with random selection of input, let's say is required. This could be, in my opinion, let's say interface fuzzing, where the fuzzer just randomly generates CAN or Ethernet messages. And the fuzzer has no knowledge of your internal software structure or what kind of internal state machines you have implemented. Okay. Then for the second highest, two highest, let's say CAL levels, CAL3 and CAL4, which requires an adaptive selection of inputs. And this is where we also want to use instrumented fuzzing, because the fuzzer adapts input generation based on a feedback loop, based on the source code. Yes, that's instrument fuzzing. Yes, it's instrument the source code that gets coverage information. Based on that, he can, let's say, tweak with an AI-based methodology, for example, variables, yes, that I come one time in the if condition and one time in the else condition. And so I can adapt the input here to generate smart input. Okay. Yeah, now I explained to you very much from process perspective here, why we investigated that with instrumented and interface fuzzing, because on ISO 21434 and ASPICE, but I personally would never, let's say, introduce a tool, yes, into our department when the tool would not be successful here, because the main aim of all the processes is to improve our product. This means make our products more secure. Okay, and also from this point of view here, instrumented fuzzing looks very promising. As it found 1,600 bugs in Office and also 29,000 bugs in Chrome. Yeah? Okay. However, we must see these are all POSIX or Windows-based operating systems, and our products in our business area, user experience, mostly have software running on ClassicAutoSAR, which is an OSIC and safety-based operating system. Okay, this was also the reason of our collaboration. Therefore, we invited different fuzz testing tool vendors in January, February 2022 to us in Babenhausen, and where we should evaluate their tools directly on our product here to see, does it hold what we promised? Yeah, because all the slides every time look good, but we need to see if it works. And here in February 2020, I also met Sergey and his team to evaluate instrumented fuzz testing and to figure out if it could help us in detecting buffer overflows, causing many, many critical security bugs vulnerability. And now when I think later on it, it was really, let's say, great timing, because as we know, 1 month later, Corona started, and then we could not do this evaluation, let's say. Okay, and it's obvious, I would say, that the tools, from the tools we evaluated in 2022, that code intelligence tool works, because otherwise we both would not sit here and would give the talk together with Sergey. Okay. Yeah, now we want to come, let's say, to the second part of our presentation here. How actually did we apply instrumented fuzzing by code intelligence in UX? For that, I hand over to Eckhard.
Yeah, okay. We have here also a short overview slide. How is the evaluation of our products? Now we are starting in former times with smaller displays for climate control units. Now we are, as I mentioned in the introduction, we are developing this driver information and comfort information displays where we have security assets included, like odometer value, velocity, safety relevant parts. And in the future, and this is what we're seeing on the horizon, it will be get more assets with, for example, integration of a camera module for pay on demand for app stores, for car access, and also for starting engine like functionality examples. And this is the reason why we are looking always for improvements or extensions of cybersecurity, and this is then also why we are choosing instrumented fuzzing for our driver information display. And with that, we would like in the technical part of this fuzzing, and Michael will take over again.
Okay. First, I want to tell you what kinds, let's say, of fuzz testing exists and which we are using for UX projects. So as the first kind, unit tests with address sanitizer, it's not really testing here, but however, you can still benefit from using the address sanitizer infrastructure by co-intelligence by just simply rerunning your unit tests. This is CI fuzz framework. This, for example, could be used for Cal1, where fuzzing is not needed. However, you still can identify with that approach with very less effort and budget buffer overflow caused by unit tests. Okay, then the second approach is module fuzzing. Here's also this picture. This is very similar to unit module testing. And since your module under test, in this picture is the application software component. Let's say it depends on other modules. Let's say you need to create stubs and mocks on which the module you want to test depends. Okay. So in contrast to unit testing, where the tester feeds the public API, and let's say with concrete values, for example, 5002 for the mass add function, and verifies that the result is correct, 5002. And module fuzzing here, the CI fuzzer generates the input automatically for the public API. So an example could be that CI fuzz selects integer max and 1 for the mass add function, and then it checks that no value above overflow happens. But just imagine in our use case, int max and 1 would cause an overflow. Now the value would be -1. Okay. Now imagine this use case would be used to update our odometer. So now we have our security asset odometer and our security goal. So odometer value should not decrease. But now with this value overflow, US attacker could suddenly decrease it because it becomes -1. Now you add anything on it and 10 more values, and then it's 9. So this means it's possible with that to manipulate your odometer, let's say, approach. Okay, then we come to software in the loop fuzzing, which is presented here, which is very similar to software system testing. Both are sending CAN or Ethernet messages to our ClassicAutoSAR software system. But since instrumented fuzzing is running on a high-performance server on Linux, let's say we need a microcontroller abstract layer simulator to run our software pseudo system on it. So this means the part which is MCall, let's say, specific, which is provided by the processor, let's say, developer, which is the gray part which we simulate, and all the rest of the software system we call pseudo software system, because the gray part is taken out. Okay, so for me, this is the preferred testing way for ISO 21434 for the following reasons. So first, Continental, as Eckhard showed, is selling complete displays here, ECU systems. And for that, the security project manager is responsible for the overall system, including all software parts, by also different suppliers. And this means that all the source code, which is part of the final delivered ECU, should be considered by fuzzing. So also a software in the loop fuzzing approach automates finding bugs as early as possible, because the MCall, let's say, layer is standardized, which is coming from the hardware, and you do not change software so often, but also rest in your software system. You add new features, so you get changes in the interfaces. Therefore, let's say module fuzzing, you need then to update your test setup. Okay, and then also for tier 1, it's more complex, to execute all modules of a module fuzzing, because you must be sure that not a module has a critical buffer. This is very hard for tier 1, because the modules here, let's say for the AutoSAR stack, for example, are coming from tier 2, let's say vector and electrobit. They do not give us, let's say, the test stubs to us here. So this means we would need to create for all these delivered components our test stubs again. Okay, and then also one common, let's say, error which we identified is for ClassicAutoSAR, you generate code. So your module might be actually very well developed, but your interconnection of the modules, let's say, is not working so good because some parameters in Traces or DaVinci are wrong. This is also what software in the loop system fuzzing tags, since it works on the entire, let's say, generated source code. Yeah, so content fuzzing I will show later on an example. Okay, yeah, and now I pass over to you, Sergey, to continue with that slide.
Yeah, I mean, if we are looking at the instrumented fuzzing in the product development lifecycle, you basically see the typical V model. You would see the typical V model inside from the automotive. So basically, you have the verification phase, and at some point, when you got all your requirements and start actually coding, at some point you will be also starting testing. And I mean, everyone is familiar with static analysis, and this is the right approach. While you are using your IDE, you can get a few hints, which is good or bad style. And I mean, if we are looking at the industry, this is something which is already widely adopted within the industry. But obviously, at some point, the developers are submitting their code into the CI/CD, and there you would be running the different phases like unit testing, integration testing, system testing. And what you would realize that if you would use something like the static analysis over there, that you on the one hand would get a lot of false positives, but on the other hand, if you get the penetration testing reports, you see that you also missed a lot of things. And this is exactly where instrumented fuzz testing is pretty good, because in comparison to the black box fuzz testing approach, where you don't know what's going on, you would be always starting from scratch and you wouldn't know when to end the fuzz testing. Here, with the instrumented fuzz testing, because we have all the coverage information, we don't have to restart. We know what kind of inputs lead to very important states. But besides that, you are able to rerun the old states, you know, and basically every time you generate new inputs in a smart way, you will be seeing whether you reach new paths or not. And this is like the ideal use case, because from the development point of view, if you run your nightly tests, you would always know when to stop fuzz testing.
Thank you, Sergey, for explaining it. I also want to say, let's say that we are at UX using both here, static analysis and instrumented fuzzing, and also interface fuzzing. I think as here for functional testing, different levels. On the security side, we also have different levels to tackle different, let's say, find different vulnerabilities. Yeah, to pass an ASPICE assessment, every test strategy, also our instrumented fuzz testing strategy, should be compliant with the VDA ASPICE test strategy criteria. Okay, so it's part in the 2017 edition is in section 3412. So here you see the orange, let's say, color is the criteria you have to satisfy. This goes from A to J, let's say, and then the black part are the answers of UX here to satisfy this criteria to pass our ASPICE assessment. Okay, let's go to bullet point A. Yeah, as you see, as a firmware of the hardware security, as the name already says, is security relevant, because the firmware stores our private keys here, which should be secret. And if you have now a readout buffer overflow, let's say on a crypto algorithm, which is using this key, maybe the key will get dumped out when it's not secret anymore. As well as the keys should be authentic, yeah, only updated when it's supposed to be, yes. And we want to avoid that you update the key, let's say, accidentally, or an attacker use it via a write buffer overflow to inject its own key. Then the next firmware, which we use, is the OEM loader. Yeah, this firmware allows to update application software via the over-the-air updates inside the car. And this is also security critical, because the loader can change the entire code flash, and thus an attacker can very easily inject a new code. even if the ECU is not a security critical ECU, yeah, injecting code, the attacker could convert your display into a bot. And then the bot just would spam the entire CAN or Ethernet network, yeah, and then it's triggering deny of service attack for other ECUs because the error handling mechanism starts. Okay, it's the application software, yeah, which is the largest part of the software, because this is the software which is used to render, let's say, your graphical GUI. Yeah. This will be only pass tested by us when the ECU has safety critical functions. And let's say, or if it has very security relevant assets like in Automator. Yeah. Because the reason is based on our security architecture, the application software has no rights to modify the code flash. And so if the NVM would be modified, yeah, then we could fix our display by updating it. Let's say. So that means the update master could just reflash our display in a car. But in contrast to that, if the loader is broken, yeah, you cannot repair your ECU anymore. Then it needs to be built out of the car, sent anywhere. You need to unscrew the ECU and go to that with the debugger. And you have recourse, and this is very, very expensive. Okay. Just to save some time, yeah, we will share the slides, the PDF of it later on. Yeah, and you can also enter, let's say, some questions, let's say, to the test strategy in the chat, and then I will answer it.
Yeah, maybe there were some questions already regarding exactly this VDA ASPICE part. And one of the most common questions was, what are your exit criteria for fuzzing? When to stop?
Yeah, so first we have, let's say, completeness criteria, let's say. So if we have, let's say, a security critical function, let's assume here it's SecOC, yes, secure onboard communication, then we want to cover all public function of the entire software chain, yeah, coming from CAN interface, PTU router, SecOC, crypto service manager, interface, crypto interface, PTU router, communication end-to-end, and then it goes to the FSM application. So this means for us it was important that the test strategy fits to our V model. Yes, on the left side we have the software system design, where you have any way how the modules interact and also public functions. And then to ensure that it's all covered, we want that the fuzzer covers also public functions. Yeah. And the exit criteria is okay. Yeah, it's covered by that. Let's say also public functions or an error occurred. Okay, and then you also need an entry criteria. So the entry criteria is also very easy. We just say if I send CAN messages to my display and it replies with a CAN message, then when we run our same software on the simulator, yes, for the same CAN message, we should get the same response. But because we want to find really bugs on our hardware. Yeah.
And maybe another part going into the same direction, there is also the question, what is the fuzzing time and the data size you get in the corpus for an auto ECU, basically? So how long does the fuzzing run for types of your software if you never ran fuzzing before?
Yeah, when we run fuzzing, it's the first time, for example, because you add new features. This is normally the phased 100% software, when it only needs at most 1 day, yes, because we have a very high performance computer and the tool scales up good. This is also very efficient, so you can run it overnight. And let's say, but when later on, let's say after your 100% software is done, then you only do bug fixing. So this means you don't get new software, you don't get new functional chain, and this is what we do. What's the nice part is of the CI tool is it creates a corpus. If you have, or should I say, a finding for that, or also for the input, it generates as a corpus, and we just say we replay is the corpus. So this means also CAN messages or Ethernet messages. To reach that, we just replay, and when we see now my findings are fixed, and this goes within minutes. Yeah, this is what you can then integrate, for example, in your CI/CD, so that only, let's say, commits to the master can be allowed when your fuzz findings from 100% software becomes less. Yeah, because your aim is to come to 0, let's say, and not to introduce more. Yeah, about data. Oh, sorry.
Oh, sorry. And how to determine the completeness and the coverage of the fuzz testing there?
As a completeness is because fuzzer logs, let's say, the tools, the functions it covered. And for example, let's say we have here security-related function we want to cover. Yes, let's say SecOC. Based on SecOC, you have then here as in this chain 25 public functions which the fuzzer must cover to go through all AutoSAR levels. So it's very important so that we don't stop, for example, I don't know, in the PGU router, because then our structure is wrong and the rest we will never reach here, because then you will not find bugs in E2E. So based for every security related feature, we have based on our software systems design, a chain, let's say, how it is, as a German Workkette, and then all the public function of that must be covered. And if the fuzzer can cover it, because he generates smart input, let's say, then we know, yes, our stack is covered, and then we can stop.
Okay, thank you. I mean, there were more questions, but we will handle these at the end. Those were more or less related to that slide.
Okay, yeah, this is one picture which I promised you to show. That's content fuzzing, custom fuzzing. On the right side, you see the ECU, yes, so our display. And then you also see our outer interface, which is CAN. For example, you can send via vector, CAN-OA, CAN messages. And our ECU itself, it has different chips. For example, as a display panel, yeah, to how should I say, to show the picture when it has a timing controller to do, let's say, white point calibration and so on. It also has a touch controller where you can convert your capacity input into electrical signal. And then we have here, for example, our Traveo 2 hardware. And based on this Traveo 2 hardware, there's a microcontroller abstract layer driver. Based on that, yes, the green part is our generated AutoSAR operating system plus application software. Okay. And since for error analysis, OEM and Tier 1, yes, most ECUs have many, let's say, debug functions, yes, to check internal states. You can use, for example, read memory by address. Or also when you produce your ECU, yeah, this one, you must trigger a function to calibrate or set the registers for white point calibration of your display. So this means you have many also protected functions for your end of line diagnostic, but these are very powerful functions here. This is what you do not want, let's say, what an attacker has access to. Yes, what you don't want is that this use case happens. He figures out a CAN message, sends it, and then it triggers your protected diag functions, and when you change parts in your code configuration, and then your ECU is problem. Okay, theoretically, it never should happen. Yes, it's clear. But sometimes you have project stress, and when you get more people onboarded, yeah, this everybody knows in project life. And when people, to make their life easier, they added bypasses here, because here to add this function, you need to authenticate yourself, let's say this authentication process, and then you need connection to backend, and this is maybe too time consuming for some, and that's why we add bypasses. But this is not documented. And this is the aim of let's say, content-based fuzzing here. So we have here our Linux system where CI fuzz is running. Now CI fuzz just generates binary streams. That's why together with code intelligence, we extended, let's say, the framework so that here it can be splitted. Let's say your binary stream, when you get different binary streams, and then we have different, let's say, mutators for different protocols so that we are more efficient. For example, SPI mutator, CAN input mutator here. So the aim is we log, let's say, on this part, we use hardware loggers when we log from software system tests the messages which should be sent, and then in a smart way we mutate it. So that we get more fast, let's say, through our AutoSAR stack and more efficient. And let's say, and now if the fuzzer, yes, can reach, let's say, our protected function, here, let's say here a binary stream which represents a CAN message. And we didn't give the fuzzers private key, and we know, oh, we have a bypass, because this is what should not happen. It's similar to a buffer overflow. Yeah? With address data, you also say what should not happen. Your buffer overflow. And this is also the case. What we see. Yeah, I like this picture because you see the way how the real ECU looks like and the way how, let's say, it's done on the simulator. And then if you figure out your CAN message, you can also replay this CAN message on the real hardware. And when you see what happens here, maybe everything crashed forever and your device will not start up anymore. Yeah, and this also helps replaying, let's say, the CAN messages for acceptance of the methodology here. Because when you directly see the evidence. Okay. Yeah, now let's come, let's say, closely to the end. Let's say here we have our practical examples, what we did. On the right side, I have an image from Infineon with a Travia 2 processor. On the button, let's say you see the peripheral interfaces with the different protocols that support link CAN. Then above we have, let's say, the communication bus. Yes, where everybody can access the ROM code, let's say, or the flash, code flash, and RAM. And then we have different cores. So M0 plus core, where the HSM firmware is running. And then here it's a dual core system where we have two M7 ARM cores, where application software and bootloader is running. Okay. To fuzz the firmware of the HSM, it's the easiest part to fuzz here. So the reason is the HSM has no interrupts, no external interfaces, and it has a small code size. You can imagine like how it works here. So the M7 core says, hey, HSM, here is my byte stream. Hello. Yes, please use key number 7 and encrypt it with IS. Yes. And when it does it by itself, and when it passes it back, let's say, to the M7 core, yes, and all the handling, it's done by, and scheduling is done by the crypto service manager. So here, very easy and very good, let's say, to fuzz test. Second easy path is the application software. Yeah, it's already more complex because the ClassicAutoSAR simulator needs support for interrupts of CAN, LIN, Ethernet, SPI, and so on. But why it's easy, it has no code execution from RAM. And let's say, okay, the hardest part for us from our experience was end of line and OEM loader. So the first reason is when you have here your code flash, when you have your flash controller, is that for some pages, yeah, you can either read code or you can update code. So this means I can update code, so execute code from code flash or write it. So this means to update some code areas, you need to execute code from RAM. So it must support execute code from RAM. And that's the end of line toolbox. It's very hardware related because you check in your production, are your soldering points correct by measuring, let's say, voltage. And if the voltage is not high enough, then yeah, you have a cold soldering point. Okay. Yeah. Okay, what we are happy is that what we showed to you here is our instrumented fuzz testing strategy. The slides before, let's say, we presented it, let's say, for ASPICE assessments and also to the DECRA assessments. And yeah, we passed it, as you see here on the left side. So we got our certificate. We showed also, let's say, our report that's produced by CI Fuzz tool. Yeah, also in the cybersecurity assessments. And then we really critically looked for that. Yeah, all your functions covered. Does it fit to your software system design? Did you not miss anything? Did you not stop because you're out of budget? And we all could satisfy it, let's say, as by cybersecurity. Yeah, and also integrating the UX code intelligence fuzz testing toolchain. Let's say with our MCore software in the loop simulator, yeah, helped us to find bugs easy because we could automate it, let's say. Yeah, but for me, let's say the best thing is that our UX products are more secure, yeah, because they want every time the best for our end customers. So we fixed many bugs and now they are more secure and we hope it increases the value because yeah, you cannot manipulate, for example, odometer so easy. Okay, now let's come to you, Sergey.
Yeah, But having a look at the time, and we want to have some time for questions, we will send up a recording of the demonstration, and we will skip it for now so that you can continue with your show, because this is more interesting than simply seeing a demo. Yeah, we will, so in the chat, we are also sending a white paper out, so where we summarize the most important aspects of the ISO 21434 components. Just click on the link which you are seeing in the chat. Maybe this will help. Okay, and now back to you, Michael.
I think we have here only the conclusion now that we are coming now soon to the question. We saw, yeah, the two aspects, the compliancy of the processes, and the other one, the technical part, how we introduce it in our product. I think it was clear mentioned from Michael, we had the success from a process point of view with succeeding the CSMS certificate or the OEM ASPICE assessments we successfully passed. And also on the technical part, we presented the OEM demonstrator for the SIL fuzzing, and we got also positive feedback, and this gave us this the feeling that the trust is increasing of our customer, and for sure we see that our products are more secured. As Michael mentioned, we are not 100% sure, but it gives a better feeling, I would say. So, and with that, I would stop here, and we should raise questions now, no? Yeah. Thank you very much.
Okay, thank you, Eckhard. Thank you, Michael. We already have some questions inside the chat. One is, how does fuzz test coverage satisfy RQ1011 coverage requirement from ISO 21434? You had it on one slide, because if you look deeper, it says, if verification by testing is adopted, test coverage shall be evaluated using defined test coverage metrics to determine sufficiency of the test activity. Note 5, standard test coverage metrics can be inadequate for cybersecurity, e.g. statement coverage for software.
Yeah, this is correct. That's why also we used Hoshut as a public functions to cover it. Because sometimes if you have, let's say, platform modules, you cannot reach also the source code because of if-def and so. But for us, it was important not to miss any module here. So you also need to get, let's say, distinctions between effort you want to spend and what you can get.
Also, maybe from the reporting side on the fuzz testing, it's not just going on the statement coverage, because if you use instrumentation correctly, it's going on a branch and part coverage, so it actually goes much deeper on those kind of metrics. It's just harder to visualize, but nonetheless, you can count it and measure it, so you can always see what's actually going on. The next question is, do you also use fuzzing for precompiled firmware that you get from your tier 2 supplier, for example? As an OEM, we most of the time have no access to our supplier's code.
No, it's, we need the source code, because during the process, the toolchain instruments it. But yeah, this is also, we presented it from our tier 1 perspective. And we as tier 1 have the source code here for, how should I say, so OEM, it's different. But what we did is we showed the tooling of instrumented fuzzing to the OEM, and also with the assessment here, he can come to us and then, how should I say, see what we are doing is. So,
yeah, but in general, when we have only a library from tier 2, then we also don't fuzz this, because we cannot do it. Yeah, this is then similar. Yeah.
Yeah.
Maybe from the tooling provider perspective, it is possible to do some kind of gray box or instrumented fuzzing on a binary level for those modules where you don't have the source code. But you have also to know the risk compared to where you own the source code and can enable specific compiler flags, you will always find less bugs because it's impossible to introduce very good bug detectors. So in a way, it is possible to find it, but compared to the completely approach where you own the source code, you always will get better and more information and a higher automation. You will always need to fine tune a little bit more with the binaries. Okay, there is also another question. Is some of this applicable to model-based development? It seems that the analysis is happening on the C++ code, right?
Maybe to that, we also have a model-based approach, but based on that, at the end, we generate the C++ code. As well as that, we use generated code, because in your model, you can also change your parameters, let's say. And then if you use the generated code, we also figure out buffer overflows, let's say, which is caused maybe due to a bug by the generator itself or due to the wrong configuration. So yes.
So when you say wrong configuration, it's the wrong configuration of the model, right?
Yeah, of the model, yes. So mostly when you have model-based approach, for example, you configure all your DAG jobs, lengths and stuff, and then you generate out your routines, let's say. But and then if you put anything wrong into the model, it generates code, which leads to buffer overflows, which we also hit. Yeah, so it also is recommended. I would say especially recommended for model-based stuff, because yeah, the parameters can be wrong. This is hard to figure out.
I think so. We also received some questions before the webinar. I think you covered it quite well in your code, but maybe it just got lost. Could you reply again? Is ASPICE for cybersecurity covered when design is done doing ISO 21434? And what are the gaps if not?
Let's say ISO is the entire, let's say, V model for cybersecurity. You start with your, let's say, assets. What do I want to protect? When you continue, let's say, mapping with assets to your architecture, when you derive, let's say, from your architecture, new security controls. For example, some messages are critical, like a flashing. That's why I want to have a signature for that, or encrypted. And then at the end, you test it. And there's also what I showed on the ISO. We have different car levels, and it all first starts with the asset. If I don't have any odometer, I don't have privacy. It's just the climate control. Yes, maybe it's car 1, maybe when even it's not needed. But if I have what Eckhart showed, let's say very nice, yes, face recognition, and I can unlock the car, then of course, yes, the ISO says, please do instrumented fuzz testing, because yeah, it would be bad if you could, I don't know, generate, let's say, a mask, yes, for input from the scanner, which goes to a buffer overflow, and then the doors open. And I can steal from everybody the suitcase here. So the ISO norm are all processes, and just testing is one process. And for that, we use instrumented fuzzing to cover also the 2 highest car level, let's say, because it's adaptive. So yes, but of course, only testing is not enough here. You also need design and a good architecture. That's why we also linked, let's say, our test completeness criteria to the design of the SSD, that it's every time linked and we don't forget anything to fuzz test.
Okay, thank you. Okay, looking at the Q&A again. Maybe one question which we got in advance, and this would be the last one. Are you also doing fuzzing on FlexRay?
Oh, just to link Ethernet, and then also, let's say, our graphic protocols, since we are display.
Okay, thank you. But then, thanks everyone for attending. Thank you for the great questions and all the applause here. Yeah, have a nice afternoon or morning, depending on where you sit. Thank you very much.